So the last thing we're going to look at with logs is how to do problem solving with them. Real life situations where logarithms are necessary to answer the question. Okay? And we're going to look at a few different areas. So, and we're just going to do them all by example. So really the new thing is, how do we set up the equation? You guys should know how to start solving the equation because we've been doing those all Unit 8. Okay? Let's look at something in the business world. And I gave you guys this formula before when we first talked about exponential functions. If you want to find out how much an investment is worth after a certain period of time and given a certain interest rate and how many times interest is calculated in a year, we use this formula where A is the amount of your investment, P is the principal, how much you've invested to begin with, R is the interest rate that you get as a decimal, N is the number of compounding periods in a year, or the number of times interest is calculated in a year. If N is 1, interest is calculated once at the end of the year. If N is 2, interest is calculated twice, halfway through the year, at the end of the year again. So you actually get a little bit more money the more times it's compounded. If it's compounded monthly, how many times is interest calculated in a year? 12. Okay? Quarterly. Think of what quarter? 4. Yeah. Okay, so here we have a situation where we're going to invest $2,000 and we are told the interest rate is 7.5%. So remember, when we start calculating with it, we don't use the percent form, we use the decimal form. Compounded monthly automatically tells me that N equals 12. Or what you may want to do when you set these things up is put in everything you know, one of those you don't know. Well, how much is in the account after 5 years? That's asking for A. So A is the unknown here, which means you must know all the other things. What's the principal? 2,000. The rate of interest as a decimal, we already saw. The number of compounding periods, I already wrote. How long is this investment in for? How many years? 5. Don't confuse N and T. So plug everything into your formula. A, which I don't know, equals 2,000, which is P, times 1 plus R, which is 0.075, divided by N, which is 12, raised to the N, which is 12, times T, which is 5. And that's a nice one because that's just a straight calculation. You just got to know your order of operations. This, and all of these would be in the calculator section. You would be allowed to use a calculator for all of these. Okay, a little hard to do this mentally or without a calculator. So if I do, I'm going to do this first. I'm going to do this division and then add 1. So 0.075 divided by 12 is 0.00625 plus 1. This whole thing works out to 1.00625. Raised to the 12 times 5, well, that's the same as 60. It's a little hard to do this all in one step on your calculator. It's possible, but you'd have to use parentheses in certain spots, so it could get a little confused. Next, I'm going to do the exponent, and I'm going to multiply by 2,000 after to get the answer. So 1.00625 raised to the 60th power times 2,000, and then round to 2 decimal places because it's money. We get $2,906.59. What's that? You should have this little button on your calculator. Or some of you may have this or this. Yeah. What's that? Decimal? How many? Oh yeah, because it's money. Right? Money is always 2 decimal places. Always. Oh, you would get it as part of the question. Yeah. Yeah. You don't have to memorize any formulas for these. You'll be given the formula and you just have to be able to use it properly. Okay. The next question. Same formula. Reading the question, which one of these 5 letters is the unknown? P? It says how long? T. T is the unknown. What's the amount? Well, I'm told 4,000. The initial or the principal is still 2,000. The decimal, or sorry, the rate, interest rate as a percent is still 0.075, and interest is still calculated 12 times a year. So using my formula, instead of A, I write 4,000. Instead of P, I write 2,000. 1 plus instead of R, I write 0.075 divided by instead of N, I write 12. Raised to the 12 times T. When the unknown is in an exponent, when the unknown is in an exponent, that tells me I'm going to have to use logs. Okay. Because I sure as heck can't make the basis the same in these. It's way too complicated. Okay, so we've got to solve for T. Well, first of all, we had this before, it was 1.0065 to the 12T. Yeah. Yes. The next step, right? We want to try and get the power by itself, the base and the exponent. So if there's something being multiplied in front of it, get rid of it by dividing. So I end up with 2 equals 1. You can use the parentheses or not, doesn't matter now. Is that. Somehow, we have to bring this T down in front of the, bring it down instead of it being in the exponent. Remember how to do that? I need to log both sides. could have written that as a new step. Because remember one of your log laws? What can I do with the exponent now? This is the power law. If I take the log of something raised to some exponent, that's the same as the exponent times the log of the argument. So I can bring this in. So that means I'm going to get log 2 equals 12t log 1.00625. I've brought the t down from the exponents. Now I just have to divide away what's beside the t, right? Because isn't this times 12? How do I get rid of that? Divide 12. How do I get rid of the times log 1.00625? Divide it. So I'm going to divide 12 log 1.00625, and it's going to cancel that and that. Which means I got to do the same thing to the other side. So I got to divide log 2 by 12 log 1.00625. Now I need my calculator. Remember, when we are dividing, we got to think parentheses around the top, parentheses around the bottom, and then divide. So you should put those in when you do it on the calculator. So for example, what I would do, open parenthesis, log, and then it opens another set. So I enter 2, I got to close the 2, and then close the one in front of the log. Divide, open parenthesis, 12, log, it opens another set, so I put 1.00625, close that off, close the big parentheses off. What do we get? 9.27, yeah. So T, you can say T is crossfire action. Is that passing around to the nearest? No. So it doesn't matter how many decimal places you write. And don't forget the units here, though, because there are units in this, years. So that means it's going to take a little over 9 years, 9.25 years, for you to double your money from 2,000 to 4,000. Okay. Let's look at another business one. Something that happens to equipment in manufacturing businesses. The equipment depreciates. Also happens to vehicles. In other words, it loses its value over time. And you can calculate the value of a vehicle, the depreciation after depreciation, or the value of some equipment after depreciation using this formula, where V is the value of the equipment, P is the original value of the equipment when you first bought it, whether it's equipment or a vehicle. R is the rate of depreciation. Okay, I should put it, I don't know why I put the interest rate, it should be depreciation. Okay? Depreciation. Is the time in years. So again, let's just answer each question. Well, what are the letters in the formula? These three. The question tells me what's the value of the vehicle after 4 years. Which one is the question mark? D. Which means you must be able to tell me the other ones. So here we're doing a vehicle. What's P? 17.5. What's R? 0.16, 16% is a decimal. And what's T? 4. So this one's pretty straightforward. I don't have to do any logs here. I just have to calculate the right-hand side. 17,500 times 1 minus 0.16 raised to the 4th. Or in other words, 17,500 times 0.84 raised to the 4th. And remember your order of operations. Do the exponent first, times 17.5 after. 0.84 to the 4th times 17.5. And it's money, so you should get $8,712.75. Okay. Part B. How long to the nearest year will it take for the vehicle to depreciate to a value of 3,000? What's the unknown? T. The value of the vehicle after depreciation is 3,000. The original value of the vehicle is 17.5 still. And the rate of depreciation is still 0.16. So you should be able to write your equation now. 3,000 equals 17.5 times 1 minus 0.16 to the t. That tells me it's an exponential equation. I'm not going to make the basis the same, so I've got to log. I'm going to have to log. But I can make inside the parentheses a little bit easier. Before I log. Can I make the right side a little easier to deal with before I log? Divide this away. Just get the power by itself. So divide 17.5. Divide 17.5. So 3,000 divide 17.5. I'm going to start to cheat now. Oh, I'm on the exercises, that's why. Oh, there's my lesson. Yeah, it's a big one, right? It's like 0.171428,571 equals, I don't need the parentheses anymore. Now what? Log. Because when it's in log form, because of the power law, I can now bring the exponent t in front as a multiplication. It means the same thing. So this becomes t log 0.84. This is still 0.17, yada, yada, yada. Now I brought the t down. Now I can isolate it by division. Dividing by. What gets t by itself? What do I divide by? Log 0.84. divide log 0.84. Sorry, forgot the log here. So when you divide those two logs by each other, it says to the nearest year. Anybody got it? 10 years. Okay. Science world, which some of you are happily familiar with. Okay. I heard a couple students doing one like this yesterday. The measure of acidity of a liquid is called the pH, based on the amount of hydrogen ions in the liquid. The formula for pH is negative log of H plus, where H plus is the concentration of hydrogen ions in moles per liter. Thanks. Anyway, here's our formula. It's pretty straightforward. There's only two unknowns, the pH and the H plus. What am I given? Which one? H plus, 0.02. So the pH is under. So therefore pH equals negative log of 0.02, and that's a pretty straight up calculation. 1.7. We'll just go 1.7. Okay. Next one.
You have to say multiple years.
Oh, thank you.
No, wrong.
Oh, it doesn't have.
I thought
Way to go, Juliana. That's what happens when you skip a it.
I never skipped that lesson.
Well, statistics is technically a type of math. If you want to go there, you know, just maybe some advice. You can't win. You could try, but I'm just giving you a heads up. We can go.
Okay.
All right. A lake affected by acid rain has a pH of 4.4. A person suffering from heartburn has a stomach acid pH of 1.2. How many times greater is the hydrogen ion concentration of the stomach than of the lake? Well, that means we gotta find the pH of each one. Sorry, we gotta find H plus of each one, and then figure out how many times bigger one is than the other by division. Right? I mean, how many times is 100 bigger than 4? 100 divide 4, 25 times. Right? Okay, so we got to do 2 here. So the lake and the gut. Our formulas are going to look like, well, we're given pH this time. We don't know H plus, so it's going to look like this. And for the stomach, it's going to look like this. Notice I don't have to log both sides, it's already in log form. Do you see anything in this equation before we actually figure out how to solve it that is somewhat bothering you? Is there something that kind of bothers you a little bit? It's what? The whole question? Okay. There's that. Yeah. I want a positive. Life is better. So let's just do that. That's much easier to deal with when the log is constant. And the same thing's going to happen with this. Like notice, if ever you want to change a negative to positive, just change everything in the equation, change its sign. So if it's already positive, change it to negative. If it's negative, change it to positive. You don't have to show to divide -1. What's the base of the log? 10. We need to keep that in mind, and we're going to have to use that. I got a different type of log equation now. I can't log both sides and then get a variable by itself using the power law. What do I do when I have a log on one side and a number on the other? You got to change it to exponent form. To get h plus by itself, let's change it to exponent form. 10 to the -4.4 will equal h plus. Right? Because we do the old, this raise, that would be my little symbol for raise, equals that. (1.2) equals the hydrogen ion concentration for the stomach. Now remember, I want to find out how many times bigger this is than this. I don't need to actually find these on my calculator. To find how many times bigger, the hydrogen ion concentration of the stomach is than that of a lake. I divide this by this. Do you remember what we do when we divide powers that have the same base? What do we do with the exponent? What happens to the base? They don't cancel. What happens to the base? Like what's x to the 4th times x to the 5th? X to the 9th. What happened to the base there? It stays the same. So the base stays the same, and what do I do with the exponents? Subtract. So it's -1.2 subtract -4.4, which changes to plus, so it's 10 to the 3.2. That's it. You don't have to go any further. You can leave it in that form. Okay? If you want to, it works out to about 1,585 times greater. So this, this is not what you did. No? What did, is that what you did in chemistry? You've never done, no one has ever done this in chemistry? It's what? And what? Anyway. Good talk. Next example. Okay. An earthquake in Vancouver has a magnitude of 6.3 on the Richter scale. An earthquake in Japan has a magnitude of 8.9 on the Richter scale. How many times more intense was the Japan earthquake than the Vancouver earthquake? Using this formula to find the magnitude of an earthquake, we take the log of the intensity of the earthquake divided by the intensity of a standard earthquake, which we don't know. So again, we got to do 2, and then we got to divide Japan by Vancouver. So Vancouver. So we are told for the Vancouver earthquake, it has a magnitude of 6.3, and that's going to be the log of whatever the intensity of the Vancouver earthquake was, divided by the intensity of a standard earthquake. For Japan, everything's the same except we do 8.9. Okay. Well, we're not given a base, so we have to assume that it's 10. Remember, I don't know AO either, so therefore, 10 to the 6.3 is going to equal log A over AO for Vancouver. 10 to the 8.9 is going to equal log. Oh, no, it's not. It's A over AO. What am I doing? We're getting rid of the log. Now remember, I just want to find out how many times bigger this is than this. So in this question, it doesn't matter what AO is. Because if we take the intensity of each earthquake and divide by whatever the standard intensity is, we're still going to get the same proportion. So it really doesn't matter what they are. So don't even worry about, just leave it there. Because we're only asked to find how many times bigger. So to find the number of times bigger, it's 10 to the 8.9 divide 10 to the 6.3. Now, what would you do in chemistry? After the tears? What would you do? To find out how many times bigger something is than the other? Okay, all right, fair enough. Which is 10 to the
Oh, actually do it?
sure. 2.6, yeah. Okay. All right. I only want to start the natural log. We're only going to do 3/4 of the next page. Okay. just in the table. So many times, these type of problems where something is growing or something is going down in value are called exponential growth and decay problems. Okay. So for an exponential growth, something's gaining in value at an exponential rate. Why? Because we use exponents. If something's going down in value, and I'm just thinking of something in value, then it's decaying, but it's still an exponential decay. And it only, remember when we calculated interest, we would calculate interest like 1 time a year annually, 2 times a year semi-annually, 4 times a year quarterly, 6 times a year semi-monthly, or no, semi-monthly or bi-monthly? No, I think it's semi-annual. Thank you. Good job. 12 would be monthly. Okay. So, but what happens if it goes continuously? When it goes continuously, a funky number comes up, like pi. We all know that pi is 3.14. We're going to get a number that's called E. Anyway, E never repeats or never, E never repeats or never ends. Therefore, it's called an irrational. Okay? The only thing, I'm just going to show you where the E comes from. Let's say you have $1 and you want to invest it. And you find this place that's going to pay you 100% interest rate per year. You want to invest more, but they won't let you. They say, no, sorry, only $1. That's why we can't let you invest whatever you want. That's why we're giving you such a great interest rate. Okay. How much would you have after 1 year if interest was calculated annually once a year? You would have $1 times 1 plus, what's 100% in decimal? 1. Divide 1, raised to the 1 times 1. Right? Because you invest $1. The interest rate is 100% or is a decimal 1. Interest is calculated once a year because it's annually. And the number of years we invested for is 1. So when you do this, it's going to work out to 2, which makes sense. Because if you invest $1 at 100% interest for a year, you double your money. So that must think it's going to grow like crazy. Semi-annually, n equals 2. This time, we're still investing $1. The interest rate is 1, except now this is 2, raised to the 2 times 1. And when you do this whole calculation, you get $2.25. Well, it didn't seem to grow as much that time. I mean, I got more than double my money, but I thought I maybe would have got, I don't know, closer to triple my money. I don't know. Quarterly. Interest is calculated 4 times. Everything stays as 1 except for n. When you do all that and calculate it out, you get $2.44. Okay, it's still growing. I mean, it must, if I invest it, like, the more this increases, I must be getting way more and way more. So at some point, I'm going to be getting like $5, $10, something. 100. N equals 12. Now I'm just going to give you the answer. Now this would be 12 instead of 4. 261. Daily. Therefore, interest is calculated 365 times in a year. I'm actually going to give you more decimal points because it works out to $2.71, but then so do these ones. So I'm going to give you some more decimals. $2.71, and then plus, if you kept going with the decimals, 147. Sorry, I put too many ones in there. 71457. Hello. Hourly. How many times? 365 times 24 hours in a day. Whatever that is. It's a lot. It works out to 271, and then I get 813. So it's still growing. Not very much, though. I mean, I thought it would go higher. Wouldn't that make sense? Per minute. This times 24 times 60. An even bigger number. You get $2. $71828. That didn't grow by much at all. I got 2.718 now. Okay. Notice that it's not really climbing very much. The climb is slowing down significantly. So my next one, if I did per second times another 60, I'd get 2.718, and then maybe, I don't know, 20 or 19 or something like that. It'd be even closer. And closer if I went, what's after second? Nanosecond? What's the smallest unit after second? Haven't you guys learned that somewhere? Millisecond? Anyway, if you kept going down like that, if you did it continuously, constantly being recalculated, constantly, it's going to approach a number that never repeats or never ends, called E. So we say that E is approximately 2.718. Just like we say pi is approximately 3.14, E works out to approximately 2.718. So E is a number when you get, if you grow something continuously at 100%, it will approach E. That's how it comes from. Just like pi comes from, you take the circumference of a circle and divide it by its diameter. The more exact you are, the closer you get to 3.1415, whatever. I had a 14159. I had a 5 years. Some students, I don't know, in middle school, they memorized it to like 25 or something like that. No, didn't do that here. I don't know. I've got students that say, I used to know it to 25. Okay. So we could end up with formulas of continuous growth or continuous decay, and that often happens in the sciences. Okay, so what we'll do on probably Monday is we'll finish up the rest of this.